Hello students, back with more on impedance. Now we're going to apply the rules I talked about in the previous video to what's going on with transistors. To remind you, we're assuming that Zn is given by this operation and Zout is given by this operation. That is, we find some Vn and we change it and we look at the responding In to get Zn, or we apply some change in the output voltage and we get a change in the output current to establish Zout. So when I apply these to transistors, what I want to point out and emphasize is that Zn and Zout for transistor amps really comes from the fundamental relationship between the collector current and the base current, or equivalently the emitter current and the base current. That is, they depend on each other by this quantity called beta, which is the current gain or current amplification factor for the transistor. This is what really controls the impedances in transistor amps. So here I have drawn a basic, simple transistor amp, and I'm only going to look at it in terms of what I would call the core impedance issue. I have some source that is attached to the input of the transistor. It has its own source resistance, and I have some other load attached to the output of the transistor, and it has its own load impedance. This particular amp is an emitter follower. Now the emitter follower amp is the amp that we usually use to fix impedance. So we use it to fix impedance problems. Now, the input impedance of an emitter follower is pretty much the same as the input impedance of the other kind of transistor amplifier that we have, which is the common emitter or voltage amplifier. So part of this will apply to that amplifier as well. However, the output impedance of the common emitter amplifier is different than the output impedance of an emitter follower. So let's look first now at this problem in terms of a loop equation. So I'm going to write a loop equation, and the loop equation I'm going to write is essentially going from the source through the source resistance, through the base emitter, and then out through the output. So that loop I can write in a loop equation as follows. I can write that this has a value V0 minus the current through Rs, which is the base current, times the resistance Rs of the source, minus the VBE drop between the base and the emitter, which I will just go ahead and write in. This is the emitter and that's the base. This is the collector. And then minus the voltage drop across the load, which is the emitter current times the resistance of the load. And I'm going to set that equal to 0. Now some of you may have noticed that there is at this point no emitter resistance in this circuit. It's all from the load. If I actually have a more normal circuit, I would put a emitter resistance here, and I'm going to call that Re. This would be connected to the minus power supply in order to allow the transistor to have some quiescent operating, that is, some operating without any signal being applied. So if, not here, if Re is a lot bigger than RL, then I can ignore Re for the purposes of finding the impedance. And the reason is combining this resistor here and this resistor here, this one and this one, would be to put them in parallel with each other. And if you have this resistance in parallel with that resistance and this one is a lot bigger than that one, this one dominates. So you don't have to worry about the other one. So I'm going to ignore it in these calculations, and I'm going to use this formula here as my core formula to calculate impedances. So let's move on. I'm going to rewrite that formula, which is V naught minus IB times RS minus VBE minus IE times RL is equal to 0. Remember what I'm looking for is I'm looking for delta V in versus delta I in and delta V out versus delta I out. Okay. So starting over here, I'm going to take differences, and I'm going to say delta V naught minus delta IB times RS minus delta VBE minus delta IE RL is equal to 0. Now I have to ask the question, what am I after? Let's go for input impedance first. So Zn, remember, is equal to delta V in divided by delta I in. Delta I in this case, is equal to the change in the currents of the base. So that's that quantity right there. And we will note that the voltage, delta V in, to the actual transistor circuit is not equal to delta V naught alone, but delta V naught minus delta IB times RS. This whole thing is equal to the change in input voltage to the transistor circuit. Sketch this quickly over here. That's my RS. This is going into the transistor. Okay, and I'm interested in what is the voltage between that point there and that point there. That's delta V in. So that's going to include the change of voltage drop across RS. On the other hand, I know that delta IE is going to be equal to beta plus 1 delta IB. And that is basically beta plus 1 times delta I in. So I make those replacements in this equation up here, and I would get delta V in minus delta VBE minus beta plus 1 times delta I in times R sub L is equal to 0. Okay, so this gives me one intermediate result. Now, under the assumption that we had originally about transistors, and that is we assumed that delta VBE was equal to 0, I have my preliminary result that delta V in minus beta plus 1 delta I in times RL would be equal to 0, or Z in is equal to delta V in divided by delta I in is equal to the resistance of the load boosted up by beta plus 1. So this would be sort of one core result in our simplified model. Now, if I don't assume that delta VBE is equal to 0, that is, if in the Ebers-Moll picture, I have the result that the current in the collector is equal to some constant, which does depend on temperature, times e to the VBE over VT. If I take a delta IC, what that's going to do is that's going to bring down a 1 over VT times IC. And I'm going to call this quantity 1 over little re. So that 1 over little re is essentially the change in, I missed a step here, so that's going to be delta VBE. That delta VBE, the E then, is related to delta IC by this 1 over little re, or I can write that delta VBE is no longer equal to 0, but is equal to little re times delta IC, which is very close to little re times delta IE. So if I don't assume that this is equal to 0, I'm simply going to add another element. I'm going to add this little piece right here. So then what happens is that in the case of the Ebers-Moll picture, Zn becomes not just RL times beta, but RL plus little re times beta plus 1. Now, what is often confusing for many students is the fact that the transistor that you're working with has extra stuff. That is, that there may be a bias network. So if I draw the picture of the transistor now, including the bias network, so here I have my emitter follower, and I'm going to have RE over here. And I'm also going to attach a bias network with R1 and R2 and put that into the picture, and then maybe I'll have a capacitor over here to couple it. Now it gets a little bit more complicated because essentially the core, that is, if I think of this piece right here as comprising the core, that core gets added an additional parallel resistance of the Thevenin equivalent of the bias network. And if you're not close to signal frequencies, you would have to have the impedance of the capacitor in series with that. Most of the time, you can ignore this. But very often, you cannot ignore this. This becomes a big part of the input impedance. So with the bias network, Zn becomes now R1 in parallel with R2 quantity in parallel with the RL plus little re times beta plus 1. Now this is a little more complicated, but mostly it's messy. That is, it's not hard to understand. It takes more work to work out the deal. So it's not uncommon for this part to be big and this part to be less big. And so what you find is that Zn is very often dominated by bias network. But don't worry about this so much. You need to just deal with it when you encounter it. Think of the core result right here. This is the most important in terms of understanding how impedance or input impedance works on transistors. Okay, that's enough for this one.